Okay, so for this week, we will be going over colligative properties. And we're talking about colligative properties. Sorry, my handwriting is horrible in there because I can't get my iPad to work. When we're talking about colligative properties, these are what we call the collective properties. So these are the properties of a solution. So, oops, the properties of a solution. So we looked at the idea that a solution is a mixture, and when we make a solution, we don't have any reactions that occur. So we're not, when we're making the solution, we're not causing a reaction to occur. And that's why the property is changing. We're just taking the properties of our solvent and we're slightly changing it. So in particular, we have 4 different types of colligative properties. So we have what are called, so we've got what's called boiling point elevation. So the idea here is that if you have a solution, the boiling point of that solution will be slightly higher than the boiling point of the pure solvent. And then we've got freezing point depression. So again, the idea here is that if you have a solution, that solution's freezing point will be depressed or lower than the freezing point of the pure solvent. Then we've got vapor pressure. Oops, that's the wrong thing. There we go. Vapor pressure lowering. So the idea here is that if you've got a solution, that solution is going to, at a given temperature, have a lower vapor pressure than the pure solvent, which kind of goes along with this boiling point elevation. If we're increasing the boiling point, it's because we have to get more of the solution or more of the liquid into the gaseous state in order to get to that boiling point. Because our boiling point is the point at which our vapor pressure is equal to our atmospheric pressure. So if we're lowering our vapor pressure at a given temperature, we're going to have to increase the temperature to get it up to boiling, past what it normally would be. And then we also have osmosis or osmotic pressure. It's not like a specific name for this colligative property, but our osmotic pressure is going to increase for a solution. So if we're thinking about osmotic pressure is the pressure that a solution exerts when it is undergoing osmosis. It is also considered the pressure that needs to be applied to stop osmosis. So that's the 2 ways we look at osmotic pressure. A solution that has a large concentration of particles, of solute particles, will have a higher vapor pressure than a solution that has lower concentration of osmotic or of solute particles. We have equations that we're going to use to relate each one of these. Give me just 1 second. I'm going to actually bring this up. Nope, that's not right. So let's start looking at the equations. So these are our equations. I'm trying to avoid writing if at all possible. These are our different colligative properties. Remember, boiling point is going to be elevated. It's going to go up. Freezing point is going to go down. Vapor pressure is going to go up, and osmotic pressure is going to go up when we make solutions. Our equation for boiling point, this right here is the difference in boiling point from the normal boiling point, or the difference in the boiling point from the pure solvent. That's going to be true for this one and this one. So that delta T is the difference in the boiling point or the difference in the freezing point from that pure solvent. This I is called the Van Hoff factor. So that Van Hoff factor, that describes the number of particles that an electrolyte breaks down into. So kind of a review of Gen Chem 1, when we're talking about electrolytes. Electrolytes are going to completely break down into ions when dissolved in water. So that I represents how many particles it breaks down into when it dissolves in water. A electrolyte will be based on stoichiometry. A non-electrolyte will have an I of 1. I equals 1 for non-electrolytes. And then the I for weak electrolytes will be somewhere between, it would probably be a little bit lower than 1, so somewhere between 0 and 1, so which is, oh sorry, a little bit greater than 1 is what I meant to say. So the I for will be greater than 1 for weak electrolytes. So there'll be more than 1 particle, but not quite to the value of like 2 or 3. Okay, so let's look a little bit. Oh, sorry. I'll get back to I in just a second. This right here is our Raoult's law. And this describes how the vapor pressure of the solution is related to the mole fraction of the solution, which is right there. So that's supposed to be our mole fraction, that chi that we looked at last Thursday. And then this is the vapor pressure of the pure solvent. And then this is our osmotic pressure equation. This is a symbol for osmotic pressure. This I is the same I that we have in the first 2 equations. This M is molarity. This M right here and here, those are both molality. But this M right here is molarity. And then this is our gas constant based on pressure, because we're dealing with an osmotic pressure. So this is going to be the 0 point. Sorry, it's going to be the 0.08206 liters times by atmospheres divided by mole times by Kelvin. So that's the R constant that we're going to be using for this one because we're talking about pressure. So we use the gas constant for a pressure, or the gas constant that includes pressure. Okay. By the way, if you have any questions, let me know. Okay. So these are the equations that we actually use for these values. So let's look at our Van Hoff factor a little bit more. So our Van Hoff factor, this is, again tells us how many particles a substance is going to break down into. So if we think about an electrolyte like sodium chloride, in the solid state, it looks like one compound, but when we put it into water, it's going to break down into its ions. So it's going to produce sodium ions and chlorine ions. So in this case, if this goes on without any issues, the ideal I for this number would be, or for this equation or this salt would be 2. We had something like Mg3PO4 2 magnesium phosphate in the solid state. And we put that into water. This one is going to break it into 3 magnesium ions and 2 phosphate ions. So we're going to have a 3 there. And then a 2 here. And this down here would give us an I of 5 because of the 5 particles this breaks down into. But again, anything that is a non-electrolyte, so our regular covalent compounds, are going to have a I of 1. Anything that is a weak electrolyte, that's going to be our weak acids and our weak bases. So like hydrofluoric acid or ammonia. The examples of weak acid and weak base. They would have an I greater than 1, but less than 2. However, we will not be able to determine that directly by looking at the substance. We just know that it's going to have an I greater than 1. So for covalent species, so not acids or bases, we're going to assume an I equal to 1. For weak acids and weak bases, the I can't be determined directly. And then for electrolytes, which are going to include ionic compounds, strong acids and strong bases, I is going to be based on the chemical formula and how many ions the substance breaks down into. Okay. Let's see any questions, so I'm going to keep going. If you do have questions, please throw them into the chat. Okay. I'm thinking what else we want to go over. There's actually not a lot in this module. It's got calculations. So this is a much more calculation heavy part of the module. Oh, I guess, yeah. The next thing we can look at is going to be Raoult's law. So we talked about that very briefly when we're looking at the equations. But with Raoult's law, we're going to be looking at solving for our vapor pressure based on a mixture. So we're going to use the mole fraction of the solvent and multiply it by the vapor pressure of that solvent to solve for is what I'm looking for. Yeah. Okay. So we're going to be using this equation right here. So this is the vapor pressure of the pure, or the vapor pressure of our solution, mole fraction of our solvent, vapor pressure of the pure solvent. And that's how, if we have, this is the equation we use for non-volatile solutes. Meaning that the solutes themselves will not contribute to the vapor pressure because they are not volatile, meaning they don't go into the gaseous phase very easily. We do have another equation that we use if we do end up with a volatile, two substances being mixed together that are volatile. And that's going to be this equation right here. So in this equation, you have your two different liquids being added together, and you multiply the mole fraction of the individual substance by its vapor pressure plus the mole fraction of the other substance by its mole fraction, and you add those two together, and what you end up getting is something like this, where, oh, well, that didn't work. Try that one more time. Okay, there we go. Something like this, where your vapor pressure of your first solvent or first liquid, this is your vapor pressure of your second liquid, it's going to be a weighted average of those two vapor pressures. So if you have all the first solvent or first liquid, it's going to be that liquid's vapor pressure. As you add in your second liquid, your vapor pressure will, in this case, decrease because the second substance has a lower vapor pressure, but it's going to average out to be somewhere between the two. And then if we're at 50%, then this will be the actual just average between the two vapor pressures. I think those are the big topics that we are going to be kind of covering this week. Again, we don't have, it's not a huge module. There is a lot of math in it. But the concepts themselves are not too involved this this time. Do you have any questions before we kind of go for the day? Okay. Well, I'll see you guys tomorrow. Thank you so much.